Okay, last meeting, we were on the topic of adsorption, and we're supposed to continue with the adsorption isotherms. So that's where I'm going to share that part of the set of slides to you. Okay, so I could see here that it's already shown in your end. The part of the set of slides on adsorption, and this is on adsorption isotherms. Now, what are these adsorption isotherms? So when we speak of adsorption isotherms, these are curves, or one is a line relating the equilibrium concentration of a solute on the surface of an adsorbent. So that particular equilibrium concentration is represented as small letter Q, and it is being related to the concentration of the solute in the liquid with which it is in contact with. Now, the adsorption isotherms, we're only limited to these three as per our discussion. So it's the Friend-Buch isotherm, it's the Langmuir isotherm, and then we have the simplest of the three, which is the linear relationship between Q and C, which is this one. Now, if I'm going to present to you the different equations, okay, I will just not project this one. This is big, though. The linear isotherm corresponds to the equation of a line, and as such, the relationship between Q and C is linear. It's a line passing to the origin because it does not have any y-intercept. As for the Friend-Buch isotherm, this is the one in which you have, I think, 2 or 3 sample problems in our reference book by Jan Kuplis. Now, this resembles the rate law in kinetics. So you have here the rate comparable to the Q, you have the constant K, and you have the concentration dependent term here raised to N. In this case, your K and N here, the same K that you see here in the linear isotherm, and in the same K in here are all constants. They are the adsorption constants, and their values are extracted from, just like in kinetics, from empirical data. The same thing with the N. Okay, now the last one, which is the Langmuir isotherm, has the appearance of the Q with the subscript maximum. So I'd like to project this one. Now, this represents the maximum adsorption capacity of forming a single layer for your adsorbent. So that's your Q max. So since it is the maximum adsorption capacity, this value is also a constant. It's not dependent on the variables Q and C. So your constants are simply your K and your N. Now, we defined already what Q is. So Q is the concentration of the adsorbate in the adsorbent, or the concentration of the solute that adhered on your adsorbent, and N is a constant. Okay, so these are the 3 different adsorption isotherms. So the problem would ask you specifically to express the relationship between Q and C in any of these isotherms. So it will not leave you to guess on what particular isotherm are you going to base any of your calculations of. So the problem will make it plain and simple to use. So if it will mention that your relationship between Q and C has to be linear, then it would be the simplest of the 3 in here. So if it's the Friend-Buch that you're going to look for, or the Langmuir, it is also going to make mention of such. Okay, so these are the 3 adsorption isotherms. Please go back to our general reference book by Jan Kuplis as to the specific examples on the use of the isotherms or problems that use this particular isotherms, because we have that present in your textbook. Then we go to the adsorption equipments. So our adsorption equipments could come in any of these 3. So one is the fixed bed adsorbers. So this utilize a stationary adsorbent to filter streams. So the important properties here include the pressure drop and the life expectancy of the adsorbent. Now, these are important, that way we can predict the life of your bed itself. That's the reason why your adsorbents, whether it's in specifically in fixed bed adsorbers, needs to be regenerated from time to time. So this is the simplest of the three. So it is simple and relatively inexpensive. So easily fabricated. Most common comprising scheme, which is consisting of a pair of adsorbers. Now you have a pair of adsorbers here, class, because once the uh, adsorber from one batch, or let's say you have two batches, if once the adsorbent rather in one batch is already saturated, you need to have it regenerated. You need to take out the solute that adhered on it and regenerated. So it has it would be the next set of adsorber, or the next adsorber that will process your um, feed, whatever the feed is. While the other one is being regenerated. So that is why if this is the adsorber that is being utilized, they always come in pairs. Now, the number of adsorbers here are selected based on optimization of overall process operation and cost benefits. Now, the application ranges from large industrial operations now to remove harmful volatile organic carbons to small consumer uses, the very simple example of which are the filters and the gas masks that are being used. So they are fixed bed adsorbers. Now, as to fluidized bed adsorbers, so this utilize a more complex moving fluidized adsorbent to filter the stream. So it is your adsorbent bed that is being fluidized. So achieved by including, this is achieved by not including but inducing a stream velocity high enough to suspend the adsorbent particles. So the velocity itself of the feed that is to be processed, what I mean is the feed that contains the solutes that need to be adsorbed on the adsorbent, its velocity is so designed that it will keep the adsorbents floating, or it will keep the adsorbents afloat during the process of adsorbing. So you can see in here that it is inducing a stream velocity high enough to suspend or to keep afloat the adsorbent particles. Now, one downside of this is the higher energy cost compared to fixed bed adsorbers. Now, the behavior of fluidized beds, however, is much harder to predict since not all characteristics of the adsorbents and even the feed that needs to be processed are not known. So much of the process is much of the things that is relating to the factors that affect the adsorbency of your solute in your adsorbents are not known, especially operating conditions. So that makes this particular technology not so easy. Now, this requires a larger chamber and usually only implemented in high volume industrial applications. So if there's a large volume of feed that needs to be processed, then the fluidized bed adsorber is the one to use. Now, the third type of the three is the moving bed adsorber. So adsorbent can be kept to a minimum in here. So heat transfer is better compared to fixed bed adsorbers, though it's more complex, more expensive than fixed beds, and attrition of adsorbent particles is something to consider. Over time, as it is being used up, and since the bed is moving, there is attrition. When you speak of attrition, class, it is the reduction in the efficiency of how your adsorbents adsorb the solute on its surface. So over time, not that it gets to be saturated, but in terms of how efficient it is to adsorb the solute, it is decreasing, or there is a reduction in its efficiency. That's what attrition here means. Okay, now we will not anymore have a break in here because that was a short discussion on the adsorption process on the adsorbers and the isotherms. So we will go to liquid-liquid extraction, or simply extraction. Now, this is a process in which we separate a component from a liquid using another liquid phase. So you have two phases here, both are liquids, and one is the feed, the other one is the solvent. Now, it is very important that these two phases are chemically different. Now, the transfer of component from one liquid phase to another will, of course, be driven by uh, the deviation from thermodynamic equilibrium. So once equilibrium is reached, even though uh, there is no stopping in the transfer, but the transfer from one phase to another back and forth is just the same, referring to the rates. So there won't be a net transfer of the mass from the feed to the solvent phase. Now, separation here is according to the difference in the physical and chemical properties. Now, samples of which are polarity and the hydrophobic or hydrophilic character of your feed, especially if your solvent is just pure water. Now, in the process of extraction, this is very important, you produce the solvent-rich stream, we call the extract. So some problems does not say that the extract phase contains this much or the extract phase has this much of concentration. So the solvent phase layer is the extract and the water phase layer is the raffinate, or the solvent-rich layer is the extract and the water-rich layer is the raffinate. So processing the feed and the solvent produces these two layers afterwards. Now, applications could be removal of acetic acid from water. So in this case, you are removing acetic acid, which is a contaminant. Now, this is achieved by using an organic solvent. Another process that could be an alternative to this is distillation. Another one is the removal of high molecular weight fatty acids from vegetable oil. So in here, you are recovering a desired component, and that's your high molecular weight fatty acid. Now, another alternative to this separation is vacuum distillation. However, this is, of course, energy intensive. So as an engineer, you will have to choose whether you use vacuum distillation, which is energy intensive, or you use a solvent, but you have, of course, to think of the cost of that particular solvent and the manner in which it could be reused or recycled. Now, separation of penicillin from fermentation mixtures. In here, your desired component is penicillin. And the metal separation in mining, in processing the mined ores. So metal separation from aqueous solution. So the metals here are your contaminants. So you take them out of the water solution. Okay, more on this you can read also in your handbook as indicated in the slides at the bottom of the slides. Now, there are two main classes of solvent extraction equipments. It could be as simple as a mixer settler, a vessel which has a form of agitation. Now, the extract is the layer on top, the raffinate is the layer below it at the bottom, and of course, you separate the extract by means of simple decantation if it's small, if it's just a small container or equipment, or it could be a case of overflow. So, your extract is being separated from your raffinate by manner of overflowing. Now, another equipment is in which we have the mixing done by the fluids themselves. So this is in the case of multistage extraction, in which the velocities of the feed and the solvent phases are the one that enable them to get mixed. So we only have these two solvent extraction equipments. So when we speak of the feed in our extraction, it has the solute, the one we're interested in, and it is the component that is present in the least amount. Now, it is being carried by what we call as the carrier solvent. Now, that's the majority of the components in your feed, and there's actually, in our case here, we only have two components because our problems here in separation processes is only limited to two component system. So the one that is present in the least amount automatic is your solute when you speak of the feed. Now, when we speak of the solvent or the extraction solvent, or otherwise known as the separating agent, it is that immiscible or partially miscible. liquid added to the process to create a second liquid phase uh, for the purpose of extracting one or more solids from the feed. Now, your extraction solvent or your separating agent is comprised of the extractant, the one responsible for taking out the solid from the feed, and the diluent. Now, sometimes a modifier may be added to your diluent to increase the solubility of the extractant on it or to enhance the effectiveness of the extractant. But it's an added cost in some processes. That is why it's not being considered, unless otherwise there's no other way to separate or increase the effectiveness of extraction. Now we go to the other terms here. So when we speak of the equilibrium stage or the theoretical stage, so this is the device or a combination of devices that accomplishes the effect of intimately mixing two liquid phases until equilibrium concentrations are reached. Then we physically separate the two phases into clear layers. Now we have what we call here the separation factor, equivalent to relative volatility in distillation. Now we have the partition ratio, the distribution constant, or the distribution coefficient. This was also discussed in the topic of gas absorption, and its definition is comparable to that in gas absorption. So the solute concentration in the extract phase divided by that in the raffinate phase after equilibrium is attained in a single stage contactee is any of this, because they mean the same. Partition ratio, distribution constant, or distribution coefficient represented as K. Now, for dilute systems with straight equilibrium lines, the partition ratio is equal to the slope of the equilibrium line. Now, we have the loading capacity. The importance of having to know these terms is if the problem is asking for the unknowns in this form, not asking you as to our representation in extraction. So that is why I'm discussing this. So when we speak of the loading capacity, that's the maximum concentration of the solute the extract phase can hold before the two liquid phases can no longer coexist. Or this is the time in which your solid will start to precipitate already as a separate phase. Now, more on the partition ratio that was discussed in the previous slide is the high partition ratios that generally allow for low solvent use. So as much as possible, we want this K value to be high. That way, we will have less solvent to use to effect the same amount of separation. So less solvent use, smaller and less costly extraction equipment utilization, and lower cost for solvent recovery and recycle. So this is what I mean, that especially if the solvent is costly, it is a thing to consider that the solvent can be recovered and recycled or reused in the process. So a very high or a high partition ratio would lead to this low solvent use, smaller and less costly extraction equipment utilization, and lower cost in the recovery and recycle of the solvent. Now, what is the desired value for these partition ratios? So in the order of 10 or higher. So as much as possible, it should be 10 or higher than that. That way, operating your extraction system will not be costly. Now, let's go to solvent properties. Now we go to solute selectivity. So it is important not only to recover a desired solute from the feed, but also to separate it from other solids present in the feed and thereby achieve a degree of solute purification. So we want as possible our solvent to be selective in taking out a particular component in the feed. That way, there won't be subsequent unit operations processes to have your particular solid separated from other components in which your solvent was able to take out from the feed. Now, the selectivity of a given solvent for a solute I compared to solute J is characterized by the separation factor. Okay, the separation factor, which is compared to the relative volatility in distillation. In extraction is simply the ratio of the partition ratios. The ratio of the partition ratios of component I to J. So meaning the mole fraction of component I in the extract phase over the mole fraction of component I in the raffinate phase divided by the mole fraction of component I, rather, no, not mole fraction, by the way, because this is liquid-liquid extraction. It's mass. Mass fraction of component J in the extract phase over mass fraction of component J in the raffinate phase. So your Y is extract, your X is raffinate composition. So that is why its representation here is still alpha, the representation of relative volatility in distillation. So a value of 1 or higher is preferred in here to achieve an increase in solute purity on a solute-free basis. Then we have to consider mutual solubility. So low liquid-liquid mutual solubility between feed and solvent phases is desirable because it reduces the separation requirements for removing solvents from the extract and the raffinate streams. We don't want our carrier solvent in the feed to be also partly miscible or miscible with our solvent, the solvent or our extractant responsible for taking out the solute from the feed. That is the case, another series of unit operations again would be needed to separate your carrier solvent from your extract phase. So that has something to do with mutual solubility. Now, recoverability, something to do with your solvent being reused. So the economical recovery of the solvent from the extract and raffinate is critical to commercial success. Then we have to consider also density difference. The difference in density between the solvent and the feed phases on the order of 0.1 to 0.3 gram per liter is preferred. So within this range. A value that is too low makes for poor or slow liquid-liquid phase separation and may require the use of a centrifuge. A value that is too high makes it difficult to build high dispersed droplet population density for good mass transfer. And that is, it's difficult to mix the two phases together and maintain high hold up of the dispersed phase within the extractor. But this depends on the viscosity of the continuous phase. Now, there's a mention here about the dispersed phase and the continuous phase. Although if you can recall in our discussion last year, this could be interchanged, but oftentimes, class, your continuous phase is your feed phase, the one that contains the solute. The dispersed phase is your solvent phase. Again, they can be interchanged, but if the problem is not stating that you do it otherwise, that's how it's supposed to be. Okay, so continuous is the feed, dispersed is the, dispersed is your solvent. Okay, safety. So solvents with low potential for fire and reactive chemistry hazards are preferred. This is a given. Interfacial tension. This is something that we consider when we design our extraction equipment already. This one is our lambda, or is it sigma? I'm not familiar with the name of the Greek symbol. The interfacial tension. So preferred value for this interfacial tension in the feed phase and the extraction solvent phase generally are in the range of 5 to 25. In the sample problems that were given you then, most of the values are 20 or 25. Oftentimes, it's 20 to 25 dyne per centimeter. Now, systems with low values of interfacial tension easily emulsify. So then, if they will emulsify, it will be hard to separate. For systems with very high values, that is greater than 25, dispersed droplets tend to coalesce easily, resulting in low interfacial area and poor mass transfer performance unless there is a form of agitation in your equipment. Okay, so take note of the interfacial tension. Industrial hygiene has something to do with the handling of the solvents. So solvents will have or should have low mammalian toxicity and good warming properties as desired. So low toxicity and low thermal absorption rate reduce the potential for injury through acute exposure. This has something to do with handling the solvent. As for the freezing point, this has something to do with those industries that are not in our region, those that has the winter season. So solvents that are liquids at all anticipated ambient temperatures are desirable since they avoid the need to freeze protection and or thawing of frozen solvents prior to use. Okay, so it's not a concern here in the Philippines. So multiple use as much as possible. We want our extraction solvent not just to be limited in terms of use in our extraction process, but could also be used in the other parts of the processes in the plant or in other areas of processing in the plant. Now, in terms of environmental requirements, so solvents must have physical or chemical properties that allow effective control of emissions from vents and other discharge streams. Simply put, dapat ang inyong mga effluents easily, shall I say, containable should there be any problem to those emissions or effluents. So preferred properties include low aquatic toxicity and low potential for fugitive emissions from leaks or spills. Now, it's also desirable for a solvent to have low photoreactivity in the atmosphere and be biodegradable so that it does not persist, of course, in the environment. Then we have materials of construction. It should not be so, shall I say, limited that materials of construction for your extraction equipment should be really intended only because for that particular equipment because of the solvent that is being used. So it is desirable for a solvent to allow the use of common, relatively inexpensive materials of construction. Now, number one on the list actually, second to safety, not number one, is availability and cost. So your solvent must be inexpensive, not that expensive and easily acquired. Or solvent should be readily available at reasonable cost. Okay? Again, all of this can be read in that section in your handbook. Now, as for equilibrium relations, we have components A, B, and C in our two phases. And we know that our variables here are still temperature, pressure, and concentrations. They are determinants for the state of equilibrium. I'd like to ask, can you still remember what is ABC in extraction? What does A mean? What does B mean? And what does C mean in extraction? Can you still remember? A refers to the what? B refers to the what? C refers to what? Because in your X and Y representation, when you label your X and Y with these subscripts, it's important that you recall what is A, what is B, and what is C. Because most of the time in here, if you're not designing your equipment, you're just using material balance. So what's A, B, and C? Are you still there? What's A, B, and C in extraction? A is the what, C is the what, B is the what. Why is it that, isn't it means that you mentioned that there should be only a two-component system? Correct. The two-component system that I mean is two components in your feed and two components in your solvent. Now, why is then that you have A, B, C in here? What's A, what's B, and what is C? Thankful for this one in the inbox. All right. Thank you for this, Joshua. Your A is your solute. Your C is the solvent, the one that is responsible of taking out the solute from the B, and B is the inner part of your feed. Oftentimes, it's your water. Okay, most of the time, it's just water. Okay, that's it. So, but you are interested in A and C. You're not that interested with the inner part or the water. Okay, now, this is the equilibrium triangular diagram, something that is unique for extraction only. Other diagrams are, of course, having curves, having XY, the X and Y axis. This one does not have those, but rather, if I look at it, it has three different lines in which we're able to read out the concentration. So this may be trivial or very simple, but let's see. So if you want to read on the horizontal axis, you are reading the B. So it's 0 to 1.0 B from left to right. If you're reading from this side, right side, going up to the apex of the triangle, we're reading the C, and that's your solvent, 0C to 1.0C. And if from the apex of the triangle going down to on the left side, going down to the beginning portion of your horizontal line, that would be your A, your solute concentration. Okay? Notice that it's not any more mass fraction, rather mole fraction, but it's now mass fraction because we're talking of extraction. Gas absorption has the mole fraction. Okay? Now, this one is an example of a liquid-liquid equilibrium data for acetone water methyl isobutyl system. Your acetone is your solute, your water is the B, acetone is the A, and MIK is your C. The water phase here and the MIK phase here, you need, if you can recall what we did then, I don't know if we did this graphically, but in face-to-face we do this, that way the student would understand how is this table related to this diagram. And they were taught how to write the diagram from the table. So the one that you have here at the bottom is based on what you have here on the last two columns. Just in case you will encounter a scenario wherein you are to interpret and take information from a table or an extraction equilibrium data like this. So unique naman ang extraction because you have this pair of data, or rather diagrams. They come in pairs, that way you can correctly give the information that is sought for. Of course, from this particular diagram. Now, going back to what I said, so these last two columns are the two information you need in plotting this curve in here. Let me project. So you have here the water layer composition, and you have here the ether layer composition. The ether layer composition is your extract layer. The water layer is your raffinate layer. We're going back to the table. You have here the water phase and the MIK phase. So water phase is your raffinate, MIK phase is your extract layer. So if you ask to construct that one or associate this one with this, if you don't have this one, you can, even though you're not allowed to interpolate, but you don't have any choice. You interpolate from any of the data that you have in here. Okay, so this and this will result to this curve that you have, whatever system that may be. And in the last three column, in the first three columns rather in here, you need only class the MIK and the acetone. You only need the C, this is the C, whatever is your solvent is, and your A, your solute. That way you can come up with this curve here. Okay, let me project. So this curve is as it is because you have plotted mass fraction of A against mass fraction of C. And here, A and C. So you get it from this two columns here. Water you don't consider anymore. Okay, we're not interested with water. We're just interested with these two. Now, other triangular diagrams would look like this for a system in which you have partially miscible components. You have your one-phase region here. You have your two-phase region here. The thing that separates these two is the this curve. You have here the plate point. Call this the plate point. And we call this the equilibrium tie line. By the way, this curve is the phase envelope. I was thinking of what it's called, just like this one is also referred to as the phase envelope. Now, in here, another triangular diagram. If this one is for, sorry, if this one is for partially miscible components, this one is for partially miscible liquid pairs, not components, but liquid pairs. So the example that is given in here is for B and C to be completely miscible with each other, and A and C completely miscible, but the resulting layers only partially miscible. So instead of having a phase envelope that looks like the one that was shown to you that is paired with a rectangular diagram below, it's like this. You have two one-phase regions, one on top and one at the bottom, and you have this two-phase region here in between. Okay, just in case you'll be asked to interpret. Although I'm sure you would be able to see samples of this in your handbook as well. Now, if we have a single extraction system, if it's John Couples that we're referring to, we're using the LO, B sub n plus 1, B1, and L1 representation. But if it's just McCabe, this would be your 1, and this would be your 2 here. Just like what I mentioned to you last year, I'm not sure if I have mentioned it, you can turn this clockwise and you will have a vertical representation equivalent to that of the gas absorption and stripping processes, to be able to associate the representation of John Couples with McCabe. But this is 1 here at the right, and this is 2 in here. Okay, we will not anymore discuss the graphical interpretation, because anyway, you won't be doing that when you take your licensure exam. So that's how we represent the schematics, and this is how, of course, we make our material balance. We add the streams that are being processed. We add the streams leaving our extraction unit. So this is your extract, the V1. L1 is your raffinate, LO is your feed, V sub 2 is your solvent. When you make a balance on a particular component, only make one component as a basis. You don't do mass balance. So you don't do rather component mass balance on more than one component, because you will just be going back to the original equation that you have if you intend to solve any unknown. So just one component balance based on a particular component. Say if it's A, then it's A. If it's C, it's just only C. This is comparable to what you have also in gas absorption and stripping. Okay. Now, what are the common types of equipment for liquid-liquid extraction? This is the mixer settler extraction. You have your mixer here and you have the settler here. The extract overflows on top, the raffinate is withdrawn at the bottom, or it could be something like this. Oftentimes in the industry, we have the spray extraction tower. The heavy liquid, we call this the continuous phase, is introduced on top. The light liquid, which is your solvent, this is the dispersed phase, is introduced at the bottom. It's bubbled up against the heavy liquid that goes down. It could also be in this manner. The heavy liquid is sprayed downwards, and the solvent phase is flowing countercurrent to it going upwards. Okay? Any of those scenarios. It's explained also as well in your textbook, so please read again. So when do we use the spray extraction tower? When rapid, irreversible chemical reaction occurs, such as neutralization of waste acid. Or simply put, if there are irreversible chemical reactions that occur, the spray tower is preferred. It can only have 1 or 2 stages. It's low cost, but take note, it's rarely used, because it's very rare also, class, that in extraction process, there will be a corresponding chemical reaction that is expected. As much as possible, we select a solvent that is unreactive to the feed or to any components of the feed. It should only separate or take out the solute physically from the feed without having any chemical reaction occurring. That is why it's rarely used, the spray type extraction tower. As for the packed extraction tower, so this is more efficient, used when only a few stages is needed and when interfacial tension does not exceed 10 dyne per centimeter. In our discussion a while ago, the desirable interfacial tension is 5 to 25. So 10 is still within the range. So choice of packing material is based on the feed. The continuous phase is your feed. And uses preferably random packing over structured packing. So since it's a packed tower, just like gas absorption, we can also have packed towers in gas absorption. We can also have packed towers in distillation. So in here, in packed extraction towers, the random packing materials are preferred. Now, the height equivalent to a theoretical stage equivalent to the HETP in gas absorption is greater than mechanically agitated towers. So if you have a mechanically agitated tower used for extraction, its HETS is smaller compared to the HETS that you'll be getting from packed extraction tower. Now, when we go to design, I'm sure you already have enough of this flooding thing, but when we design our extraction tower, it's also based on the flooding. When is our tower flooded? So what is this particular condition of flooding? So this occurs when increasing either the flow rates of your solvent or feed phases makes both of the phases to leave the continuous phase outlet. So both of your phases, the dispersed phase and the continuous phase, will leave the tower bottom. So it is recommended that the design flow rates be set at 50% of the flooding condition. So take note, if it's gas absorption or stripping, our diameter for the tower is based on 60% flooding. For extraction, it's 50% of the flooding condition. So where do we get this particular flooding velocity? It's taken from this chart, the flooding correlation chart. You can also see this in your handbook. It has an equivalent in the handbook, a flooding correlation for packed towers. Now, the thing that you need to determine in here would be the VC and the VD. You have two unknowns, right? So if you can recall our discussion as well last year, you have two unknowns here, but you can have another relationship between this VC and VD taken from the flow rates of the continuous and the dispersed phases as given in the problem. So you have now a ratio between the two, and having this also as unknown, we'll be able to solve the unknowns VC and VD using two equations with two unknowns. Of course, it's a given that you should be able to have this. You should solve for this one first so that you'll be able to get this one. Okay, the value on or the x coordinate. Now, where are you going to get these parameters here? Empirically determined. So they're taken from here. Some are given in the problem itself or stated in the problem itself. So you will have this table. You have to go back to this table wherein you have the packing materials as the basis of taking those very important parameters that you need to solve first. This one is very comprehensive in the handbook. This is just but taken from Jan Cookies. Now, that's it. So you will determine the flooding velocity. Once you have the flooding velocity from that particular velocity using the volumetric flow rate. Using the volumetric flow rate of the feed, not the solvent, of the feed, you'll be able to get the cross-sectional area of your tower or your column. Once you have the cross-sectional area, of course, you can determine the diameter. Okay, in terms of using this particular flooding correlation diagram to come up with the size of your extraction tower. Now, there are problems that does not give you the interfacial tension. You can still solve the interfacial tension, and there's a sample problem on this as well from Gian Kupli. So you can solve the interfacial tension using this particular formula. This has a downside, however, because this one will only hold for an equation in which the argument of this ln, you have an ln function here, the argument of the ln function has a range of value of 0.0004 to 0.30. Meaning if it's lesser than this one or greater than this one, the value that you will be getting will not be anymore acceptable. Either it will be negative, there's no interfacial tension that is negative. Okay, so then this particular formula will not be any more suitable. Of course, it will not be suitable because this one is empirically determined as well. So ma-work lang siya sa Sininga range because as per experiment, that's just how it goes. It will only work for this range of values for the argument of the LN. Now, a value of 1.0 for this interfacial tension indicates the complete solution of the phases at the plate point. If there's complete solution of the phases at the plate point, there won't be any separation because they will be one homogeneous phase already. And there won't be any mass transfer that could be expected from that. You'll be needing this very important conversion in the process of determining the diameter of your column in here when you use this particular flooding correlation diagram. Okay, now we go to this one, the perforated plate sieve tray extraction tower. So just take note of how it is supposed to be in terms of design. And how do we determine its tray efficiency? Since it is a sieve tray extraction tower. Now, the hole diameter here refers to the diameter of the holes in the sieve. Okay? Now, that's for the perforated plate or sieve tray extraction towers. And you have this table also that gives you the, when you already determined, by the way, if you already got the value of the V sub D and the V sub C from the two equations I mentioned a while ago, using the flooding correlation diagram, you can check the value that you got for the VD and the VC based on the type of tower that is stated in the problem. So this is the approximate sum of the flooding velocities of the dispersed and continuous phases for these particular types of towers. Again, your handbook has an equivalent of this. From this particular approximate flooding, sum of the flooding velocities that you solve, you'll be able also to determine the acceptable range of the capacity of the combined streams. And that is what would be the, if you're going to take the sum of the dispersed phase flow rate and the continuous phase flow rate, it should be within this range for spray tower, pack tower, and so on and so forth. You'll also be getting the HETS in here based on the type of tower, and you'll also be getting the overall height of the transfer unit based on this particular tower, if it's a straight spray tower or pack tower. If you need in the problem the hull, since you have the range here, what you're going to do is get the average using the lower and upper limit on the indicated interval. So 3 plus 6 divided by 2, or 0.9 plus 1.7 divided by 2, if you need the hull in your computation, or the H sub OL. Now, these are the other types of extraction towers. I leave that to you to read. Anyway, I've shared the slide to you. And I failed to mention a while ago that for extraction, I gave you a separate set of solved problems for extraction. But for the other topics, distillation, it's on the PowerPoint presentation. We have this. Just read on that so that we can save time. And these are equations. These are the equations available in your handbook for straight, equilibrium, and operating lines. Equations that you will be using in determining the number of stages. Okay? You have also the Krimser-Solders-Brown equation, theoretical stage equation. This is in John Copley's, but it has an equivalent in your handbook. These equations in your handbook. For equilibrium curves with moderate curvatures, geometric mean of the M is used. We intend to solve the number of stages for our extraction tower theoretically. So as such, hindi ito pwede magbalik sa equilibrium curve kag dito kwaon ang mga M's. So we need to take the mean, the geometric mean specifically of the M's if we have equilibrium curves, not lines. I passed this particular slide. This is in the case of multi-stage countercurrent extraction. The same principle actually. It's only represented differently. The subscripts are different, but you add still the streams that were introduced in your system of stages in your tower, and then you also add the raffinate and the extract layers, and that will also be equated to the bulk phase. And this is your A balance or component balance on C. So that's a balance on C. Now, you have here a formula that allows you to determine the number of stages without using Krimser's equation or Krimser-Solders-Brown theoretical stage equation. You can use this. It has the partition ratio K. It has the amount of solvent S naught, as you could see. You have the amount of feed F, and your X and Y are concentration of the solute on solute-free basis. It's concentration of solute on solute-free basis, meaning it's ratio. It's not fraction. Because if it's A over B, then it's only mass ratio, not mass fraction. Because mass fraction is A over A plus B. Just as an example. So concentration of solute on solute-free basis, meaning it's actually mass ratio, not mass fraction. This is taken from an equation in your handbook used in determining the number of stages. For minimum solvent flow and optimum solvent flow, you first determine the minimum. You have this figure from John Copley's to go back to in determining the minimum solvent flow. The minimum solvent flow class in extraction in terms of principle and how you find it is exactly the same as the way you find it in gas absorption. You find in this case, you find the V minimum. Okay? You find the V minimum. If you want the optimum, you first find the B minimum and then multiply it by 1.5. The range here is 1.2 to 1.5 of the V minimum. We always use the higher range of value, and that is 50% of the minimum. Or that is 50% more than the minimum. Our book, John Copley's McCabe uses the Krimser equation in determining the number of stages. And look at the representations here. It's now using simply 1 and 2. 1 bottom, 2 on top. Okay. This M is the slope of the equilibrium line. The problem oftentimes should give this if you are required to determine the number of stages analytically or theoretically. And otherwise, you won't be able to solve for what is required if it's graphical. So this one is the slope of the equilibrium line. The A, the absorption factor, it's the same thing as the formula that you have in gas absorption. I'd like you to go to a sample problem in John Copley's on how you determine the A, using the Crimson's equation in liquid-liquid extraction. Liquid-liquid extraction actually, not that it's comparable to gas absorption, but it's comparable to stripping. Comparable to the opposite of gas absorption, which is stripping. But in principle, it's just the same. It's just the opposite. Now, you can also, just like in stripping, I'd like to use the term stripping, you can also use the inert amount of the strips. So L prime for the inert, or that's the carrier solvent of your feed, and the V prime, that's your diluent in your extractant. Okay, that part, the inert part of your feed and solvent phases in extraction. So you can also use this. The way you use the equation is the same as if you're just dealing with a stripping problem. Where to find the equation in your handbook for minimum and maximum solvent to feed ratios? These are the equations. Since I have indicated it here, look it up in your handbook. That way you'll be familiar already with these equations as they are represented in your handbook. The extraction factor, these are the focus of the sample problems that I shared with you in Canvas. The use of the extraction factor in determining the number of stages, and the very simple take on extraction using McCabe's way. So you can find this in equation 23.4 in the 7th edition of McCabe. You have here the extraction factor equal to K sub D times B over L. And you have these ratios of X sub 1 over X sub O in terms of the extraction factor. And this particular formula allows you to solve this one. The fraction of the solute remaining using pure solvent in a single stage extraction. So if the problem would be asking you how much of the solute remains unrecovered, or if the problem is asking you for the recovery, you solve for it and you subtract it from 1 because you have it. This one represents the fraction that was not recovered. So you can subtract from 1 your answer from here. That would be already your recovery for your solute. So the fraction of the solute recovered using pure solvent in a single stage extraction is this one. So more on the recovery itself. This one is just 1 minus this. You have this one. Okay? As for efficiencies, overall stage efficiencies in extraction, more free stage efficiency in extraction, not anymore discussed during our discussion on liquid-liquid extraction last year. These are found on these equations in your handbook. And the overall stage efficiency related to more free stage efficiency as applied to extraction. Please look these equations up in your handbook as well. As to the HETS, the height equivalent to a theoretical stage, you may wonder why do we need to determine this one? Because with the HETS, this is your height equivalent to a theoretical stage when you have a packed extraction tower. So it's just like how tall would be your packing material for you to consider it as one stage, one theoretical stage. So the significance of the HETS is you can multiply the HETS to the theoretical number of stages. That would be now the height of your extraction tower. So knowing the HETS allows you to solve for the height of your extraction tower if you already know the theoretical number of stages using the Crimson equation or using the equation that is found in the handbook. So this one, I'm referring to this or this. So getting the end there and multiplying it with the HETS for a packed extraction tower allows you to solve for the height of the tower. I have here the link, the set of problems for you to read on extraction. I gave the separate document on this, shared it to you in Canvas already. Okay, so that's for extraction class. We still have more or less an hour. I'll give us a 5 or a 6-minute breather here. Then we'll proceed with the last 3 topics. Okay? I'm sharing distillation. The slide that you are you seeing the slide already on distillation? Share. Do you see already the slide in distillation? This is
Yes,
actually,
ma'am.
okay, this is actually the modified version of the slide that I have shared with you last year. I have also included sample problems in here already as part of the PowerPoint presentation. So this have videos, the videos that you were not able to see. As I have shared this with you in Canvas, they are raw slides as shared to you so you can watch as well the videos. Okay, but I will not be showing it now to you. I'll be going straight to the principles that are just important and fundamental. So when we speak of distillation, so we have been talking about unitary processes wherein 2 streams are being contacted or phases that are being contacted. So in distillation, initially we only have 1 phase. So in distillation, we utilize the vapor and liquid phases at essentially the same temperature and pressure for the coexisting phases and zones. So uses random or structured packings, plates, or trays to bring the 2 phases into intimate contact. The phases in here that is being referred to are the liquid and the vapor phases. Now may be operated continuously or in batch mode depending on the number of factors such as scale and flexibility of operation and solid contents of the feed. Now all components are present in both phases, the liquid and the vapor phases. Primarily because our vapor phase actually came from the liquid that was collected at the bottom of the tower and then boiled up against the feed that flows downward in our still. So vapor phase is created from the liquid phase by vaporization. Now, I'd like to have this projected that way it would appear bigger. So your feed material here, which is to be separated into fraction, is introduced at 1 or more points along the column shell. The liquid runs down the column, cascading from tray to tray, while vapor flows up the column, contacting the liquid at each tray. Liquid reaching the bottom of the column is partially vaporized and heated in a reboiler to provide the boiled up vapor, which is sent back up the column. Excuse me. The remainder of the bottom liquid is withdrawn as the bottoms or bottom product. These are fundamental in distillation and they should be understood even before you try solving problems. So vapor reaching the top of the column is cooled and condensed to liquid in the overhead condenser. Part of the liquid is returned to the column as reflux to provide liquid overflow. Reflux is the one responsible for enhancing, increasing the purity of the distillate. Remainder of the overhead stream is withdrawn as distillate or overhead product. Okay, I'll project this again. So the lighter lower boiling components tend to concentrate in the vapor phase, while the heavier ones are expected to concentrate in the liquid phase, which is our bottom's liquid. The composition of the vapor in equilibrium with the liquid at the boiling point of the liquid should be different from that of the liquid. The vapor phase becomes richer in light components as it passes up the column, and the liquid phase becomes richer in heavy components as it cascades downward. Overall separation achieved between the distillate and the bottoms depend primarily on the relative volatilities of the components, the number of contacting trays in each column or section, and the ratio of the liquid phase flow rate to the vapor phase flow rate also in each section. The column is divided into two sections, the rectifying or enriching section and the lower section, which is the stripping section. Just a review on the sections of our distilling column. This is our equilibrium diagram. So the greater the distance between this equilibrium line or curve, this one, from the 45-degree line, the greater the difference between the vapor and liquid compositions, and as such, it is easier to separate components. Okay, so we want as much to capitalize on the distance here of the equilibrium curve or line from the 45-degree line. It was mentioned in liquid-liquid extraction that the separation factor is comparable to the relative volatility in distillation. So if our relative volatility in distillation is greater than 1, then separation is possible. Now, this is the degree of separation, by the way, of the components in your original feed. And it could be also expressed in terms of the ratios of the mole fraction, if you have noticed. So you have YA over XA, Y for the vapor, and X for the liquid, divided by 1 minus YA, divided by 1 minus XA in the denominator. So this refers to the YB over XB in here, which if you don't have the mole fractions, you can use the pure vapor pressures of A and B if your system is ideal. If it obeys Rayleigh law, if you don't have X and Y, you can use the pure vapor pressure of your components, and that will allow you to determine the relative volatility of your mixture. Okay, read more on the section indicated. So as to the methods of distillation, so we have one in which vapor is produced by boiling the liquid mixture in single stage, recovering and condensing the vapors with no liquid allowed to return to the single stage still to come into contact with the rising vapor. This is the uncomplicated way of recovering the lighter components or separating the lighter components from the heavier components. One that is frequently used in the industry is method 2. The same as above, but the condensate part of it is returned into the still or the column and comes in contact with the rising vapor in countercurrent fashion, and this one is known as your reflux. This liquid is your liquid reflux. If this is the case, under method 2, this is known as fractional distillation, distillation with reflux, or rectification. So fractionation, rectification, or distillation with reflux is under method 2. So under method 1, you have equilibrium or flash distillation, you have batch or differential distillation, and you have steam distillation. Kindly read on those. And you have here more information on equilibrium and flash distillation. Please read on this. You can look at the video that is inserted, and you can view on the material balance, energy balance, and equilibrium relationship that is needed if you're given a flash distillation problem. Then you have the differential distillation. This is the lab scale distillation, the one that you perform in the lab. And we have steam distillation. Steam distillation is used if the boiling point even of the lightest component is very high, that it would like near impossible to separate from the other components, so you use steam. So that way you can lower down its boiling point. Now under type 2, you have extractive distillation, you have anisotropic distillation, and this one, okay, the fractionation. or you have the rectification or the distillation with reflux. So you could see that you have your, like to enhance this, have it on slideshow. So this is your feed. By the way, we have only a single feed in here, but we could have several feeds actually. So in your case, it's only limited to a single feed distilling problem. So you have the feed here, the vapor goes up from the liquid that was collected here and partly boiled up back into the column now in the form of vapor. The rest of the liquid is withdrawn as the bottom's liquid. Now, this is your reboiler responsible for converting a part of the liquid collected here into vapor. So, this vapor flows upwards, flowing countercurrent to the liquid that flows downward. That's your feed together with the reflux, which is also liquid. So your reflux is actually a part of the vapor that was condensed in your condenser. Its purpose is to increase the purity of the distillate or your overhead product. This is our distilling column, and it has two auxiliary equipments, the reboiler and the condenser. Okay. The most accurate way of solving a problem concerning distillation is using Ponchon-Savaret, which does not assume constant molar overflow. It is not assuming that the amount of liquid that flows downward the column is equal to the same liquid that from a particular tray rather or particular stage is the same as that amount of liquid that is introduced on that particular tray or stage. That's constant molar overflow. Equal sila. The same thing with the vapor. In the case of Ponchon-Savaret, we don't assume that one. And aside from the material balance equations that we are using, the overall material balance and the component balance, we're using the energy balance as well. And it's a trial and error process, just like the way you do it in evaporation problems. But it's more accurate. But it is suggested that the school or there is a software that is being used to have this one carried out in the undergraduate level. But in terms of the accuracy of the results or the answer to the required information in the problem, Ponchon-Savaret is more accurate than McCabe-Thiele. So the thing that simplifies Ponchon-Savaret is McCabe-Thiele, which assumes that there is constant molar overflow. And this makes the operating lines, if you can see, remember our operating lines. Our operating lines in distillation is your enriching section operating line and your stripping section operating line. So these lines will not be straight without this very important assumption of constant molar overflow. So it's best explained in here. So the liquid phase flow rate is assumed to be constant from tray to tray, which we could say equivalently the same thing with the vapor. This is our distillation column in a very simple illustration wherein we have the material balance. The feed equated to the sum of the distillate and the bottom's liquid. The W can be represented as B. And your overall component balance on A is patterned after the overall material balance. You just simply make use of the concentrations here, the mole fractions, okay, of A in the feed, the distillate, and in the bottom's liquid. This is the enriching section operating line. This is our enriching section. Your feed, this is your feed, and this is not part of the enriching section. Your feed plate is part of the stripping section. So it was only mentioned in McCabe, if I'm not mistaken. So this is how we make the total material balance and component balance in the enriching section. And this allows us to come up with the operating line equation for the enriching section. In the operating line equation of the enriching section, you'll be needing the reflux ratio, that's the R. Most problems give this one. And you'll be needing the mole fraction of A in the distillate. So that is the X sub D. This is the operating line of your enriching section, meaning this is the equation of this line. Anyways, you'll see this also in your handbook. Okay? Now, this is our stripping section in terms of the equilibrium diagram. So now it's in here. If our enriching section starts on the XT, our stripping section starts with the X sub W. I'm referring to the line that is drawn in the equilibrium diagram. Now this is your stripping section. Now the feed is still there, but it's actually really included in the stripping section. Now you have your material balance here and your component balance in the stripping section, and this is its corresponding operating line equation. Now, it's very important in distillation to be able to determine the Q, because primarily everything that you're going to solve is dependent on this Q. There are two different definitions of the Q depending on which book you are using. So if it's based on the heat to vaporize 1 mole of feed at entering condition, whatever those conditions are, per molar latent heat of vaporization of the feed, this is John Copley's description of the Q. So based on the description, you'll be using here enthalpies. As to how it's defined by McCabe, defined it differently. So it's the number of moles of saturated liquid produced on the feed plate by each mole of feed added to the tower. That's McCabe's definition. But for special conditions, like if your feed is saturated vapor, your Q is equal to 0, and it would be horizontal if it's drawn. If it's saturated vapor, if it's saturated liquid, Q is equal to 1, and it will be vertical, plotted right on the X sub F, the mole fraction of A in the feed. If your fluid is subcooled liquid, its value is greater than 1. If it's superheated vapor, its value is less than 1. If it's partly liquid and partly vapor, or a fraction of the feed is liquid and the fraction has liquid and vapor, then your Q will have a value which is in between 0 and 1. And how do you determine the Q, the actual Q, if that is the case? That portion or the fraction of your feed that is liquid tells you of your Q. So if it's 20% liquid, then your Q is 0.20. If it's 30% liquid, then your Q is 0.30. That is in the case of mixtures. For subcooled liquid feed and superheated vapor feed, we have specific equations given by McCabe. So these are the equations indicated in here. And this is the equation to be used if we are to work on finding the Q based on the latent heat of vaporization of the feed. Okay, this is it. And you have the enthalpies here defined. So the enthalpy of the feed at the dew point is H sub V. The enthalpy of the feed at the boiling point is H sub L, and the enthalpy of the feed at its entrance condition. That's your H sub F. Okay, this is the equation as given by Jean Copley's, and the equations given by McCabe I did not place here anymore. The equations that I place in here is based on the 7th edition of McCabe. So it's with the other equations from McCabe. Now your Q line equation is this. It needs the mole fraction of the feed, and of course it needs the Q value. Now, if plotted, these are the orientation of your feed line or your Q line based on its value. So I have already mentioned it a while ago. Anyway, there's no point in memorizing this because you'll see it in your handbook when you need to open your handbook during exams or licensure exam. Now, the feed plate location is determined in this manner, not in this manner here, graphically. But there's an equation that will be shared to you in a little while, how to determine it analytically. And this is how we do determine the number of stages graphically. If we want the minimum number of stages, all the operating lines coincide with the 45-degree line. So you don't see any of the 3 operating lines in here. And the minimum number of stages is determined in this manner. Okay, there is also an equation to determine the minimum number of stages analytically or theoretically. Now, we have this minimum number of stages at a condition we call total reflux. Okay? Uh, all the vapor that is condensed from the condenser is returned back into the column as such total reflux. In here. So all product distillate and bottoms are reduced to 0. It's like you don't have a distillate and you don't have a bottoms liquid. That is, all liquid in the bottoms are reboiled and returned to the tower as vapor, and all overhead condensed vapor returned to the tower as reflux, and as such total reflux. So when I explain this, I really focus on the reflux because of the term total reflux. But it's the same thing with the bottoms. So there's no bottoms liquid. It's 0 because all the liquid are returned into the column in the form of vapor. So in that particular scenario, you will have the minimum number of stages for your distilling column. Okay, how do we determine the minimum number of trays? That's using Pinsky's equation, which uses the relative volatility of the overhead vapor and the relative volatility of the bottom's liquid. We take the geometric mean of the two and substitute it in here together with the mole fractions of the distillate and the bottom's liquid. This determines the minimum number of trays analytically. You can find it in this section of your handbook. What about minimum reflux? So the minimum reflux ratio that will require an infinite number of trays for a given desired separation of X sub D and X sub W. Now, if total reflux gives you the minimum number of stages, minimum reflux gives you infinite number of stages. That's your minimum reflux. Okay, R sub N corresponds to minimum vapor flow in the tower and minimum condenser and reboiler sizes. The operating lines, enriching and stripping lines moves farther from the 45-degree line. So that the exact opposite of the total reflux. They move farther away from the 45-degree line and closer to the equilibrium line or curve, which makes the number of steps required infinite. So scenario as depicted graphically is this. So there's this part in here which would make it impossible to account for the actual number of stages, and as such resulting to a condition of infinite number of stages. The reflux ratio that will require an infinite number of stages is this minimum reflux. Okay, now we go down. This is how we determine the minimum reflux. Analytically, it's based on the mole fraction of the distillate and the coordinates of the pinch point. The pinch point, the point in the equilibrium curve wherein your Q line intersects. Where your Q line intersects or your feed line intersect. That's your pinch point. So whatever is the coordinate, that would give you the minimum reflux ratio using this particular formula. Okay, minimum reflux ratio. Now, in some cases, class, your pinch point is not the point of intersection of the feed line on the equilibrium curve, because there are instances wherein your enriching section operating line becomes tangential to your equilibrium curve. So instead of this being your pinch point, this is now the pinch point. Okay, not this one, the intersection of the feed line on the equilibrium curve. As to the optimum reflux ratio, this is based on the economic balance of the fixed cost of the tower and the operating cost. If you want to determine the optimum reflux ratio, determine the minimum reflux ratio and multiply it by 1.5. that is already your optimum reflux ratio. And this is the problem that is solved, but it will be discussed in the next slide. So I'm going to share to you the next slide. Let me just share a new one. I can't find it. Now, how do we determine? I hope you can see the second set of slides for distillation. How do we determine the minimum reflux ratio? So we have to solve the theta by trial and error using this particular formula. This is taken from John Couples. So if you're going to solve the theta by trial and error using this particular formula, you are to determine first the Q. You need the Q, and you need the alpha sub I, here, and the mole fraction of I in the feed. You see here assumption. It's because class, if you have a two-component system, you will have two fractions in here that you will add. So one will be, for example, alpha I x, let's say, alpha A XA in the feed over alpha A minus theta, plus another fraction alpha B XB over alpha B minus theta. So that makes it already trial and error because you have two fractions in which you have theta as the unknown. It is equated to 1 minus Q in here. Read on John Couples on this particular section on how you go about determining Q by trial and error. But if we have a two-component feed to process in our steel, that's the one that I just mentioned a while ago. So your alpha here and your X represents the component. Let's say, for example, component I is A and you have another component B. So you just change the I here to A and the I here to A also in the X. And you add another one for the B. As for the alpha, I mentioned the alpha, the specific formula for determining the alpha is based on John Couples. So read this particular section on John Couples on how to find the alpha. If I'm not mistaken, it's still based on the mole ratios of A and B in the feed. Okay, please check on that. Now, for determining the minimum reflux ratio, after you have already determined the theta here, you substitute it in here. This time, you're not going to have the summation of two fractions in the feed for the product of alpha and X, but rather this time you use that in the distillate. So in terms of form, do pareho lang sila nga duha. Ang kinalain lang nila iniiya sang feed, iniiya sang distillate. Okay, so more or less the same formula, but of course it's needed here in step 2 that you know already that theta from step 1. Now read section 11.7F of John Couples to be able to find or to be able to follow through the process of determining the minimum reflux ratio. Now there are also other ways of determining, ways to determine alpha here. You can base it on the average temperature of the top and the bottom of the tower, and it will be illustrated by the sample problem that is inserted here, hyperlinked in the slide. It could also be used, determined rather from Finsky's equation, and it could also be based on feed temperature. But the most, if you're going to ask me, the easier way of finding the alpha is this one, using the Finsky's equation. Because it's easier that way. You only be using the mole fractions, if determining the alpha that is. Okay? Now, you'll be able to see this particular diagram in John Couples. I mentioned that you're going to read this section in here. And I mentioned that you're going still to use the mole fractions because you have here the K class, the KA and the KB. So the KA and the KB are actually based on the shall I say, this particular diagram in here. You need the temperature. So if you have pentane, hexane, butane, I'd like to project this, it would be bigger. So if you have here heptane, hexane, pentane, and butane in your system, you just get the K value here given the temperature. You read it out from here. You have also an equivalent of this in your handbook, an equivalent diagram of this in your handbook. Based on the temperature, you'll be able to find the K values. If you don't have easy access on this, it could still be based on the Y's and the X's of A and B, because this K is actually the distribution coefficient, which is based on the mole ratios of Y and X. Y and X for A and B. Ang problema lang siniklas is dapat ina siya nga Y and X is measured at equilibrium. It's not just any Y and X that the problem is giving you. It has to be based on equilibrium. So if you have this diagram already located in your handbook, so much the better. That way it will not be a problem of having to determine the mole fractions of, let's say, A and B, both in the vapor and in the liquid phases, for you to be able to find the K's and the Ka and the Kb in here. Okay, you just simply read it out from the diagram. So if you have it already taken from in here, then you can go to determining the number of stages. That is, of course, knowing already the R sub n, because you need the minimum reflux ratio. The value of that will be substituted in this formula, and you look for the curve that will be, of course, appropriate for you to use or correctly used. And you need here the R over R plus 1 ratio. And in here, you have the ratio of the minimum number of stages to N. So actually, from this diagram, you're not going to have right away the theoretical number of stages. You're not going to have it. You still need to determine the minimum number of stages using Finsky's equation and use it in here to whatever value you got to be able to get just the N. That is theoretically without having to rely on the operating lines or the diagram that you have resulting from drawing the operating lines. You may not be able to see it. On how you determine the feed plate location, this is an equation by Kirkbride, if I'm not mistaken, and Maddox. This gives you the ratio of the number of stages in the enriching section and in the stripping section. If you have the total number of stages already, then you will have another equation relating the number of stages in the enriching section to the stripping section, because N sub E plus N sub S would be your N, your total number of stages. So from this equation, if you already got the N sub E over N sub S ratio, then together with that one, the NE plus NS equal to the N that you got, you'll be able to find the N sub E. Now, knowing the number of stages in the enriching section, for example, what you got is 10 for the, let's say 5 for the enriching section out of the total, which is 12, then your feed plate location will be the 6th, because your feed plate is the first plate on your stripping section. So knowing the number of plates in your enriching section plus 1, that would be the location of the feed plate using this particular formula. Now in the formula, you have this one, X sub HF, X sub LF. Just in case you have forgotten, this represents the high boiling point component in the feed for HF, the low boiling point component in the feed for LF. The same is true with in here. Low boiling component in the bottom's liquid and high boiling point component in the distillate. This equation was also shared by John Putis in his book. And you have this sample problem. Okay, you have graphical there, both graphical and analytical way of determining the minimum number of stages. That will also help you find the theoretical number of stages. You have the minimum reflux ratio in here. Okay, so kindly read the sample problem. Okay, we have the special cases of rectification in here. Only John Kuplis discusses this. I don't see this in McCabe. You can read on this. It's actually why I included it in here, because it's also found in your handbook. So if it's not found in your handbook, then there's really, let's say, no point in discussing it, because what you will be using in your board exam is your handbook. So expect that what you will be needing will be the things that are present in your handbook. We have here enriching column distillation. We have stripping column distillation actually also. Rectification with direct steam injection. This is actually our slide last year as well. And this is the rectification with side stream. You don't only have the distillate. Let's say where is it? We check here. You don't only have the distillate and the bottom's liquid, but you have another stream that is withdrawn in your column. If I'm going to think of this coming out of the board exam, most probably it would be just a case of a material balance. Okay, this would be the new operating line equation for this third line in here. So the usual graphical representation is you only have two operating lines. In this case, you already have three. You have the enriching section, you have this operating line for that side stream O, and you have here for the stripping section. This is in the case of the partial condenser, wherein you're going to subtract not only 1 from the determined theoretical number of stages graphically, but you're going to subtract 2 if the problem is using a partial condenser. Now, when is it in the first place being used, the partial condenser? So it's used in cases where the overhead distillate product is removed as vapor. Take note, instead of liquid. Used when low boiling point of the distillate makes complete condensation difficult. And liquid condensate is returned to the tower as reflux while the product is removed as vapor. So partial lang ang pag-condense sa vapor because it's a low boiling point component liquid. So 100% condensation is not possible. So the part that is not condensed is withdrawn as vapor. So your distillate is not liquid but vapor in the case of partial condenser. The part that is converted into liquid rather is the one that is returned back into your column as reflux. So when time of contact between vapor product and liquid is sufficient, the partial condenser is considered another theoretical stage. And it is actually the first plate in your column when it is drawn or determined graphically. So you not only subtract 1, but you subtract 2. Now, in the total condenser, of course, it's the exact opposite of this. Everything is condensed. So this is the most frequently used setup and condenses all the vapor from the column and supplies both the distillate, the product, and the reflux. Now, in this case, the concentration of the vapor from the top of the plate, which is your which is B1, coming from plate 1, will be Y1, and it's also equal to the concentration of the distillate, because your distillate is just your vapor condensed or turned into liquid. Okay, what I have here next? So in terms of tray efficiencies, I'm sure you can still remember the overall tray efficiency, ang muling pinakahapos, number of ideal trays and number of actual trays. So though not so accurate compared to more free efficiency. So for more free tray efficiency, you have now to consider the average aqueous concentration of the mixed vapor that is leaving a tray, the average aqueous concentration of the mixed vapor entering the tray. So these are all, take note, average concentration. But seldom will you encounter a problem class that determines the Morphy efficiency based on this average actual concentrations. The problem oftentimes give you the Morphy tray efficiency and lets you determine the other required information. Not that you're the one who's going to determine it based on this concentration, averaged already. If Morphy tray efficiency is more accurate than the overall tray efficiency, which is least fundamental, may ara pagid na mas accurate sa iya. And that's the point or local tray efficiency, or the Morphy point efficiency. It does not take the average of the concentration of the vapors leaving or entering a particular tray or stage, but it's really determining the particular concentration at a particular point on a particular tray. So concentration of vapor leaving a specific point on tray N. Concentration of the vapor entering the same point on tray N. And the concentration of the vapor in equilibrium with the liquid leaving the same point that is mentioned here or used as a reference with the y sub n prime and the y sub n plus 1 prime in here. Okay? Now, this is how it is. So, Morphy takes the average of this more fractions of the vapor entering a tray and leaving a tray. Now, these are things that you need to know regarding tray efficiency. So, please read on this. And how do you determine the overall tray efficiency given the Morphy tray efficiency or vice versa? Of course, the slope of the equilibrium line has to be known, and the slope of the operating line, the V to L ratio. Okay, the V to L ratio. What else? Now, determining the height of our distilling column is the same as the way we determine the height of the absorption column. Primarily because in terms of construction, pareho sila. It can be a tray, it could be a sieve tray, it could be a pack tower with structured packing or random packing materials. Okay. Now, determining the height will require the HETP and the predetermined theoretical number of stages. So the height actually class in most reference books are represented by Z for a distilling column. It could be solved using this one, the Hogg-Nag formula. And we can determine the HETP knowing the H sub OG and knowing all this. By the way, all of these formulas are found in your handbook. I've seen them there, but I think I did not place it in this slide as to where specific location or section, but I think I included in the other slide. This is for your tray distilling tower. So this is how you determine the HETP based on the tray spacing and the overall, shall I say, tray efficiency. This one. If you have the HETP already for your tray tower, then you can determine the Z if you multiply it by the theoretical number of stages. This is the summary of where you can find the equations in John Cooklis. This is the Philippine edition. The 4th edition, I think, and the Philippine edition is just the same. As for the reboiler and condenser duties, this one is found in McCabe. Now, I'd like to zero in on this particular formula, the condenser duty, using the enthalpy of the vapor leaving the top plate, the enthalpy of the distillate. Same here, it's the enthalpy of the distillate. So it needs the distillate and the reflux liquid and the amount of the vapor that leaves the top plate. The V sub 1 can be solved using the equation in McCabe because this one was taken from McCabe. So go to McCabe and check how you will use material balance to get the V sub 1. That way you can determine the condenser duty. Now, your reboiler duty needs the condenser duty. So if both is required in the problem, you need first to determine the condenser duty. Now, your reboiler duty, okay, that's your top, that's the top part of your tower. This is called the lower part. This is your reboiler duty. So it needs the enthalpy of the bottom's liquid, that of the feed, and of the distillate together with the condenser duty. McCabe is having sufficient examples on this. I assigned this as an example for you to read last year. So hopefully you did read it so that you will have an idea on how to determine the condenser and reboiler duties. Now for this heating requirements, this is one of the questions asked in the sample problem given by McCabe. How much steam is needed by your reboiler to convert part of the liquid at the bottoms that were collected as vapor? So this is your formula, the same formula you see in McCabe. I got this from McCabe. This one is for the amount, the mass flow rate of the cooling water in your condenser this time. If this one is for your reboiler, this one is for your condenser. And you have the things that appear in the formula defined in here, the variables and the parameters that appear in the formula. So these are the reading assignments that I asked you to read then. I place it in here because they will help you understand on how to use the formulas that you have here for the cooling and heating requirements, and most importantly for the condenser and reboiler duties. We don't know what to expect, so since we don't know what to expect, then we have to expect for any eventuality. So para prepared ka, then prepare for the worst. Okay, prepare for everything. So if you have the time to read, read. Okay, you read a lot. Now, let me stop sharing here. Okay, I will continue class because leaching is just short. I will share my screen on leaching. I will let you read on the slide on membrane separation because they are just separation processes without the need of streams, just like the unitary processes that I have discussed in here. So it utilizes, of course, the use of a certain membrane to have the to effect the separation of one component using another one. Okay, the one that is being used in here is not another phase but rather a membrane. That is why they are referred to as membrane processes. I'll go to leaching. That way I've covered everything. Wait, I want you just to discuss or refresh you on the formulas and the fundamentals of leaching. This is a short slide. I've shared everything to you anyhow in Canvas. So I'll share now leaching. Okay, I'm sure it's information overload already. Let me just stop sharing for a while. So for leaching, this time you won't have a liquid and a liquid and a vapor, or a liquid and a liquid, or a liquid forming the vapor. But this time you will have a liquid and a solid. So this is the extraction of a soluble constituent from a solid by means of a solvent. So you're going to take out the solute from a solid matrix. The soluble material is dissolved from its mixture with an inert solid by means of a liquid solvent. So That's leaching. A special leaching process when an undesirable component is removed from a solid with water is simply called washing. And the principle of operation for leaching is there is a need for contacting the solvent with the solid matrix, then separating the desired substance from the solid matrix using the solvent, and then extracting the desired substance from the solvent that carries it. So we contact the solvent to the solid. The solvent takes out the component from the solid matrix, and since it's already in the solvent, then we separate by extraction the solute that was taken from the solid matrix from the solvent. So leaching oftentimes is followed by extraction because your solvent here still carries the component of interest and they have to be separated. Now this can be operated by batch, semi-batch, continuous process and operates at an elevated temperature. The flow is essentially cross-current or counter-current, and the amount of soluble material removed is often greater than in ordinary filtration washing. So why, the big why? Why use leaching? Because your recovery is much higher here compared to ordinary filtration. And the properties of the solid here may change considerably during the leaching operation. So the important factors to consider in leaching is the size of the particle. As much as possible, we want to increase the surface area. That way, we'll be maximizing also the leach amount of solute. The solvent, the temperature during the leaching process, and if there's some form of agitation, in the case of thickeners, then it's also a factor to consider. Read on this and how the three important factors can aid leaching, especially temperature. So if we adjust the temperature, mass transfer is enhanced. How do we increase the recovery? One way is increasing the time of contact and increasing the surface area available for transfer. And of course, the key, of course, is solvent selection. We have to choose a solvent that will be preferentially taking out the solute, ang solute, ang kwaon niya from the solid matrix. And that should be the case because the other part of the solid should be inert to your solvent. Now, this is the process overflow. Now, in a typical leaching operation, the solid mixture to be separated consists of particles. The inert soluble carrier B, so the inert part is B and the solute A. The solvent is C and is added to the mixture to selectively dissolve A. So this is quite, that I say 100% similar to extraction. A is the solute, B is the inert part, and C is the solvent. The overflow from stage to stage is free of solids and consists only of your solute and your solvent. The overflow class is used, the term overflow is used when you're using thickeners. Okay, in the case of continuous leaching. The underflow consists of the slurry of your inert solids and the liquid in which the composition is similar to that in the overflow. So the underflow consists of the slurry of liquid similar composition in the liquid overflow and the solid carrier B. So your solid goes in your underflow. In an ideal equilibrium stage for leaching, all the solute is dissolved by the solvent. None of the carrier is dissolved. So we assume that none of the carrier is dissolved. Now, the mass ratio of the solid to liquid in the underflow is dependent on the type of equipment used and the properties of the two phases. Now, leaching is essentially countercurrent, although it could be cross-current. In industrial leaching, solvent and solid are mixed, allowed to approach equilibrium, and the two phases separated. The solvent phase called the overflow becomes more concentrated as it contacts in stage-wise fashion the increasingly solvent-rich solid. So your solvent phase is the overflow. The underflow becomes less concentrated in soluble material as it moves towards the fresh solvent phase. This is in the case of countercurrent multi-stage leaching. So for leaching equipments, we can either have percolation or we can have dispersed. So percolate, from the term percolate, the solvent is contacted with the solid in continuous or batch method, peculiar only for extreme amounts of solids to be processed at a time. So we use percolation. Dispersed solids, it is the solids that is added to the liquid. So the solids are usually crushed into small pieces before being contacted with the solvents, and this is popular when essentially high recovery rate can economically justify the high operating cost of the process. Industrially, this is the thing that is used, especially in the recovery of precious metals from mined ores. So dispersed solid is added to the liquid. Percolation, from the term percolate, liquid added to the solid. So your equipment can be fixed bed, moving bed, or dispersed bed leaching. So I'd like you to read na lang this part, that way we can proceed with the other parts in here. I'm just covering the fundamentals. Okay, I used an example here, Coral Bay nickel corporation, which is using high pressure acid leaching to take out nickel. Actually, what Coral Bay is processing is already the, shall I say, waste material na from processing, from other processing plants, mined ore processing plants, pero ginakuha niya pa dira ang nickel. This is very important, the leaching equilibrium. So solvent forms a liquid solution carrier, may be totally immiscible with. So your liquid solution, your carrier is inert to your liquid solution, the inert part of the solid that is. Some solution is normally retained by the solid, and that is why the concentration of the solution that is retained by the solid in the slurry or in the underflow has the same concentration as the solution in the overflow. When the amount of retained solution is constant in your underflow, we say it's a constant solution underflow. But the other way around, of course, is variable underflow. This exists when the amount retained is a function of concentration. So meaning, if the concentration of the solution varies, the amount of the solution that your solids retain in the slurry, in your underflow, varies as well. But if it's not affected by the concentration of the solution in the overflow, then it's a constant solution underflow. The thing here that is written. So these are the principles with leaching. So stages are numbered by flow of the direction of the solid. Kung diin ang feed gin-introduce na part, that is the stage number 1. The solid that is referred to in here is the feed. Assumption, we have a solid-free solid, or the solid-free solid is insoluble in the solvent. This is your inert solid. It should be insoluble in your solvent. Flow rate of the solid is constant through the cascade. Of course, it has to be, because it does not whatsoever interfere with the leaching process. It's just there as a matrix for the solute, and solid is porous and inert. For leaching to occur, your solid has to be first and foremost porous. That way, it will be able, your solvent should be able to take out the solid. Now, the amount of solution retained by the solid in the slurry phase is dependent on the density and the viscosity of the liquid in which the solid is suspended. Now, this one is also dependent on the concentration of the solute in the solution. Simply put, ang density kag viscosity sang liquid sa imong solid is dependent on the concentration of the solute in solution. Of course, it's dependent on the concentration. Because the more concentrated it is, of course, the density would be higher and it would be more viscous. Now, these are our very important assumptions. Solvent amount is sufficient to dissolve all. So this was mentioned in one of the slides, the solute in the entering solid, and there is no adsorption of the solute on the solid, meaning no solute remains in your solid. They are all leached out by your solvent. Solution in the liquid phase, that's your overflow, is the same solution that remains in the solid matrix in the settled slurry, which is the underflow. But one thing that sets apart leaching from the other unitary processes that we have discussed is the representation of the concentration. It has a unique way of presenting the concentration, and this is often where the students, even myself sometimes, if I'm just carried on the process of solving, that I get confused. We represent normally concentrations in the solvent or in the vapor phases as Y, and in the feed as X. In the case of leaching, it's the other way around. In your solvent, the concentration is X. Your V is solvent, it's X, and the concentration in the feed and in the slurry is Y. It has another concentration added to the X and Y, and that's the N. So we will define it later. It has something to do with the inert solid B. Okay, and we have the B, which is of course the inert solid. Okay, now leaching has something the same with extraction. It's the ABC a while ago. So the same na sila sa extraction. And the same man sila in terms of what is the manner of expressing concentration. Extraction has it in terms of mass fraction. Leaching, it's also in terms of mass fraction. Gas absorption, stripping, and distillation has it in mole fraction. So take note of that. But they are all represented as X or Y. Okay? So this is N, the third concentration that is being accounted for in leaching, and it's the amount of B, the inert solid B, divided by the amount of A and C. Unique tagid niya si leaching because the denominator in expressing concentration is not the total thing that you have in your mixture, whether it's overflow or underflow. It's simply always divided by the sum of the solute and the solvent. You don't account the solid. So in this case, it's just per kilogram of A and C. The same is true with the manner we represent the overflow, which is now X, and the underflow, which is Y. The liquid in the slurry or in the underflow has this concentration in terms of the solute. So the denominator is still in terms of the sum of A and C. And for the overflow, it's still kilograms A plus kilograms C. Okay, take note, we have X for the overflow and Y for the underflow. Your overflow is your solvent-rich layer. Your slurry is your, shall I say, your water-rich layer, or oftentimes that's where your inert solid is with. That is why it's called slurry. In the feed, we have this as the concentration of B, and we have here the concentration of A as 1. For the entering solvent, we don't have the solids and we don't have the A. So the solvent that we are using most of the time does not contain the A. Okay? Now, when we do material balance, I am guilty of this since I'm used to like just accounting for all the materials that goes in and out of my system. But when we talk of leaching class, it's just A and C that you are balancing. You have the total, I place here solution balance. It's just A and C in LO that you add together with the A and C. If there's A in the solvent that you're using. So it's just A and C. You don't account B. So if you're given a feed that has an amount of solid on it, you have to take it out. If you're going to place it together with the LO, everything that you'll be doing is wrong. It's a mistake that majority would commit because they're so used with the material balance which accounts everything. In the case of leaching, you don't account the B or the inert solid B. If you do component balance in A, this is how you do it also. Since this LO, this B2, this L1, and B1 only has A and C, so naturally you're only going to multiply it with this manner of expressing concentration in which the denominator is just A and C as well. So this is just A and C over A plus C over A plus C. Okay? The same is true with the bulk phase M. It's just A and C. If you're going to account for the solids that we have is in the feed, and it's NO times LO. And it's the same solid that is present in the slurry, N1L1, the same solid that is present in the bulk phase M. So remember, this N is B over A and C, and LO is A and C. So you get the B. The same thing in here. Okay, this is the very important material balance that you're not confused with other material balances because it's unique, very unique. The principle that is explained here, that was explained here on single stage leaching, the same principle applies for multi-stage leaching. We just have a different manner of presenting the streams because this time we already have stages. Small n is for a particular stage and capital N is for the nth stage. So this is where your leaching solvent is introduced, and this is where it is leaving your system as your overflow. So exit overflow. This is where your leached solids are found in your underflow. This is your underflow, and this is where your feed is. So remember, we number the stages as to where the feed is introduced. So since your feed is introduced here, this is stage 1. Right? So that's it, class, in terms of leaching. And in terms of principle, your overall material balance will be the same as that in the single stage leaching process. The same thing with the component balance. Now, in leaching, we did not cover, it's not part of the discussion as to the design of the thickeners, how we design the thickeners. We don't discuss it anymore. We just focus it on material balances. And it's the focus as well of this set of slides. Okay? I'm sure you're very tired already. Your membrane separation slides, I will just quickly show it to you. I'm not sure if this is the same slide that I've shared with you last year, but I have modified some, and I have included, wait, I have included videos that way you'll be refreshed, or you'll have a clear picture of what a particular membrane process is. And sometimes I really remember a student that came from the board exam saying that we need the fundamentals. As to the skill on how we use the fundamentals, it's really up to us. So it's really important that you get to understand the principle, the fundamentals behind. As to the application, actually the extent of how well you're going to apply that depends on how well you also practice solving problems. Let me share this one. So this is the membrane separation processing slides. All of the, I hope you can see it. Share again. I don't see a notification that you could see it. Okay, please read on the membrane separation processes in these slides. And the membrane processes that you see here, cross-check it with what you have in your handbook. I hope you have your physical handbooks with you already. Okay, I have included videos here, inserted videos that you can read. Okay, this is our slides for membrane separation processes. You can read those, I'm sure you will follow through even without me guiding you through it.